At its core, a ledger is a running log of transactions that tracks who owns what and how that state changes over time. Historically, maintaining this notebook required a central administrator. A bank, a corporation, or a government held the master copy and dictated its accuracy. Placing all authority in one location creates a single point of failure for data integrity. If that central server goes offline, the record stops. If the administrator is corrupted, the history can be rewritten in secret. To build a system where trust does not rely on a single human entity, the master copy of the ledger must be distributed globally. Look at this network structure. Instead of a centralized hub pushing data outward, the architecture shifts to a peer-to-peer mesh. Identical copies of the ledger exist simultaneously across thousands of independent machines or nodes. These nodes are in constant communication, syncing transaction data to verify that every participant holds the exact same version of the notebook. But if anyone can join this network, an untrusted participant might try to forge a transaction and push it to their neighbors. As you can see, the surrounding nodes immediately reject the mismatched data. Because there is no human administrator to arbitrate disputes, the system relies on strict mathematical rules to maintain consensus. Distributing the ledger successfully eliminates the single point of failure. Replacing human arbitration with verifiable math requires a new cryptographic architecture. The primary unit of this new architecture is the block. Think of it as a sealed digital container of validated transactions. Looking inside this container, we find identifying metadata. The index marks its position in history, and the timestamp records exactly when it was created. Below the metadata is the core of the block, the data payload. This holds the actual list of recent state changes, or the transaction inputs. To secure this payload, the system uses a specific cryptographic algorithm known as SHA-256. When the block's data is run through this algorithm, it generates a unique digital fingerprint. This is the hash, a 64-character string of hexadecimal code. This process is entirely deterministic. Feeding the exact same data through SHA-256 will always output the exact same 64-character string. It also features pre-image resistance. The algorithm only works in one direction. It is computationally infeasible to take the 64-character hash and reverse engineer the original transaction data. The security of the hashing algorithm relies on what is called the avalanche effect. To see this in action, observe what happens during a hypothetical attack. We run transaction A through the algorithm to produce a specific baseline hash. If we alter a single character in the payload, changing a capital A to a lowercase a, the math scrambles completely. The output becomes a distinct, unrelated 64-character string. Any microscopic tampering instantly destroys the digital fingerprint. This effect ensures the state of each block is mathematically unforgeable. A single block isolates a moment in time. To build a historical timeline, these blocks must be sequenced together. This introduces the n-1 chaining dependency. Every new block is required to contain the exact hash of the block that came immediately before it. The fingerprint of block 1 is inserted into a new metadata field in block 2. Embedding the previous hash directly into the current block's payload mathematically fuses the two containers. This continuous dependency extends across the entire sequence. Consider an attacker who attempts to secretly alter a historical transaction buried inside block 1. Because of the avalanche effect, editing the data inside block 1 forces its resulting hash to change instantly. Block 2 is explicitly programmed to expect the original fingerprint. It immediately detects the mismatch in its previous hash field. Because the data payload inside block 2 now contains an invalid field, block 2's own final hash breaks and recalculates. This mathematical corruption ripples forward. It instantly invalidates block 3 and destroys the links holding the subsequent chain together. Honest nodes on the network continuously audit the chain to verify these mathematical proofs. When they encounter the attacker's tampered ledger, the broken hashes fail to compute, and the network automatically rejects the altered history. Data permanence on this network does not require physical walls or human guards. It relies on a dependent mathematical cascade that makes silent historical tampering structurally impossible. The mathematical cascade effectively secures the data. But it currently faces one critical vulnerability: the immense power of modern computational speed. An attacker with powerful hardware could alter block 1 and simply recalculate all the broken hashes for the subsequent blocks in a matter of milliseconds. To prevent instant recalculation, the network introduces intentional computational friction, known as proof of work, or mining. This friction is implemented using a new variable inside the block. It is called the nonce, which stands for number used once. The network imposes a rule called target difficulty. A block is only considered valid if its final hash starts with a highly specific pattern. Specifically, the final 64-character string must begin with a predetermined number of leading zeros. The SHA-256 algorithm produces entirely unpredictable outputs. Discovering those exact leading zeros requires brute force guessing. Miners rapidly cycle random numbers through the nonce field. Each guess wildly changes the output hash, mostly failing the requirement. Eventually, a node discovers the correct nonce. The output hits the target, finalizing the block. This mechanism connects the abstract security of the software to the physical constraints of the real world. Cycling through trillions of guesses requires massive amounts of real-world electricity and highly specialized computational hardware. To rewrite history, an attacker cannot merely alter the math. They must physically outcompute the combined electrical power of the entire global network. This foundational architecture operates without a central authority because mathematics enforce the data structure, while thermodynamics and computational cost enforce the absolute truth.